Afternoon, this is Jessica Kim, Regional Manager for East and West European countries. Thank you all for joining with us today. As introduced, today's webinar is on bridge seismic analysis as per Eurocode. If you have any questions during the webinar, you can type it into the chatting box and we will answer your questions at the end of the webinar or contact you through your email. And if you look at the little button below the questions mark, you can download the handouts that we've uploaded and you can follow it through as we proceed. And after the webinar, there will be 5 short questions for you to answer. If you complete the questions, you can get special discount offer for Midas GST, so don't forget to fill them out as well. Should you have any questions or inquiries, you can always contact me through my email or phone call. Now let me introduce our Senior Civil Engineer, Haeyeon Lee, for the rest of the session. Thank you.
Hello everyone, this is Haeyeon Lee. Today's topic is bridge seismic analysis and design as per the Eurocode. So I would like to start the session. This chart shows the seismic design process as per the Eurocode 8. In order to go through the seismic design, first of all, we need to determine the basic requirements, and then in order to satisfy this basic requirement, we will have the certain compliance criteria such as the resistance verification, capacity design, ductility verification, and effective stiffness. Then proper seismic action will be determined among the elastic response spectrum, time history, and the design response spectrum. Depending on the regularity of the ductile bridge, the method of the analysis will be determined among those 4. Midas GST provides all the capability of those seismic analysis, and we are going to see more details how we can do it in Midas GST with the demonstration. First of all, we need to determine the basic requirement. Basic requirement is composed of the non-collapse requirement, which is in terms of the ultimate limit state check, and also we need to satisfy the minimization of the damage in terms of the serviceability limit state check. To conform the basic requirement, the design shall comply with the following criteria: resistance verification in terms of the ductile and limited ductile behavior, and the ductile verification. Plastic hinges shall be provided with the adequate ductility to ensure the required overall global ductility of the structure. And also, we will have the control of the displacement for the compliance criteria. Displacement will be verified in terms of the global level and the member level. So we will also see how we can verify this in Midas GST. Let's see more details of the seismic action. To achieve the appropriate reliability for the non-collapse requirement, design seismic action is expressed in terms of the reference seismic action with reference return periods in 478 years and importance factor. Appropriate ground conditions should be provided to consider the influence of the local ground condition on the seismic action. And nonlinear behavior due to the seismic loads of the irregular shaped bridge can be verified different from the behavior due to the response spectrum, considering the behavior factor Q. In this case, we must go to the nonlinear time history analysis. In the bridge of irregular seismic behavior, The yielding of the ductile member may cause difference between the equivalent linear analysis results considering the behavior vector Q and the results of the nonlinear response of the bridge structure. In general, realistic response of the irregular bridge may be estimated in the dynamic nonlinear time history analysis. An appropriation of the nonlinear response may also be obtained by combination of the equivalent linear analysis with the nonlinear static analysis, which is called pushover analysis. So this chart shows all the different type of the seismic analysis method. Equilibrium static seismic force method, which is using the static analysis, and the response spectrum analysis, which is the linear behavior but considering the dynamic analysis, and the pushover analysis, and inelastic time history analysis. The objective of this seismic analysis is we have different objective for the different type of the analysis. For the equivalent seismic static analysis or the linear elastic dynamic analysis, it is performed for estimating the displacement demand for the normal bridge. So we are going to perform the response spectrum analysis in order to obtain the displacement demand. After that, we are going to perform the pushover analysis in order to obtain the displacement capacity of the bridge. Also, for the irregular type of the bridge, or when we have the device for the isolation or energy dissipation, in that case, nonlinear time history analysis can be performed. So let's go more details how we can determine the seismic demand displacement from the response spectrum analysis. As per the Eurocode, in order to obtain this seismic demand, we need to use the effective stiffness. The effective stiffness of the ductile concrete component used in the linear seismic analysis should be equal to the second stiffness at the theoretical yield point. And how we can obtain this effective stiffness? It is provided in the Eurocode in this equation. So effective moment of inertia can be obtained from here, which is using the cross-section moment of inertia and the cracked section moment of inertia. From this formula, we can obtain the effective moment of inertia, and using this reduced stiffness, we can obtain the desired seismic demand. In Midas, the moment of inertia is provided for the cross section, but if we want to obtain the cracked section moment of inertia, we can also use Midas GST, General Section Designer. This is the additional module called Midas GST. For example, for this section, I want to calculate the cracked moment of inertia. So section analysis can be performed. And then from this calculation, I want to specify the required axial force, let's say 2700. Then the correct section moment of inertia can be obtained for this section. So GST will perform the mesh analysis, and then such calculation can be obtained. So after obtaining such correct moment of inertia, then we can calculate the effective moment of inertia. Let's say we calculated a certain effective moment of inertia, and we can obtain the reduction factor from this formula. So using this reduction factor, we can use this in Midas Civil for the section stiffness scale factor. So for the column, we can specify the desired reduction factor here. Then we can perform the analysis. Then the response spectrum analysis will be performed. In Midas Civil, response spectrum can be provided with the various design codes such as the Eurocode, S2, New Zealand, China, Taiwan, Indian standards. And in the response spectrum analysis, the seismic action should be performed for the major axis of the structure. So excitation angle can be specified, and various damping method is also provided. Muda combination type can be specified among the SRSS, CQC, ABS, and linear combination. And as you know, during this modal combination, the sign will be ignored. But if we want to restore the sign, we can also use this option, add sign to results. The sign can be restored along the major mode direction or along the absolute maximum value. Also, if we want to check the results for the specific modes only, there is the selection box, as you can see. So by default, all the modes we specified will be considered in the response spectrum analysis, but if desired, we can also specify the desired modes only. Modal damping, rally damping, or group damping is available, so we can specify the one certain value for the entire structure using the modal damping, or the damping can be proportional to the mass and stiffness. Or if we have the two different type of the material which have different damping ratio, in that case, strain energy proportional damping can be used. For the response spectrum analysis, certainly we need to specify the eigenvalue analysis. Eigenvalue analysis can be performed with the eigenvectors or Ritz vector, which is also useful when we need to consider the certain direction of the modes, for example, the jet direction modes. As a result, we can obtain the period of the structure and their modal participation mass in different direction. And then also demand displacement can be obtained. So from the analysis, I want to check the deformation, for example, the center of this pier table. So we can go to the results table and obtain the displacement from the response spectrum analysis. In the Eurocode, in order to determine the demand displacement, from the analysis results, which is specified as TEE in here, we also need to obtain the eta value and the mu value. Eta value is the damping correction factor, and mu d is the displacement ductile factor. In order to calculate the mu d, we need to know our period and compare it with the T0 value. So for example, I want to obtain the demand displacement in the y direction. So from this value, then I want to also know my periods in the y direction. So when the y direction is governed, the mode is force mode. Force mode period can be obtained from here. So from this period, which is this one, 0.5, and our T0. T0 can be obtained from the response spectrum function. So our response spectrum function is here. Tc value is this one, which is the end of this curve. So Tc value, we can see it is 0.5 period, 5 seconds, and multiply it with the 1.25. So T0 value can be obtained. Depending by comparing this, we can obtain the mu ud value from the equation we just checked from this. As our current period is less than T0 value, this formula has been used. So finally, TE value has been obtained, as you can see from here. For your information, Eurocode specified the eta value as using the damping ratio 0.05. Damping ratio was specified, as you can see from here, and then our eta has been calculated. So this is the final value for my demand, 0.0259. So from this procedure, as per the Eurocode, first of all, I calculated the effective moment of inertia using the correct moment of inertia. Then we have reduced the stiffness of the structure using the section stiffness scale factor. Then calculated the response spectrum results. From the response spectrum analysis, we have obtained the displacement. This displacement has been applied with the design seismic displacement by multiplying these two additional values. So finally, our demand displacement has been calculated. Then what we need to do, we know demand now. Now we want to calculate the capacity. Capacity can be obtained from pushover analysis, which is the nonlinear static analysis. Why pushover analysis is required? When do we need to perform pushover analysis? For the estimation of the sequence and the final pattern of the plastic hinge, or estimation of the redistribution of the force, or assess of the capacity curve. So from this assessment, then we want to calculate the capacity and we want to compare it with the deformation demand. In Midas 7, performing pushover analysis is not very complicated. Program will provide you all the procedure and then also either give you the global verification as well as local verification. So let's see more details. First of all, for the pushover analysis, we need to have we need to specify the global control. Global control includes the initial load. This initial load is the one applied to the structure for the self-weight or the superimposed dead load. So this gravity direction load will be specified from the global control. Then we need to specify the pushover load case. The pushover load case can be specified for the horizontal load increment, or it can be applied based on the load distribution method. Horizontal load increment is applying the horizontal force nodes and increase it step by step. The load distribution method is following the mode shape obtained from the eigenvalue analysis. In this example, we want to apply the pushover load as the horizontal load increment. So we will apply the horizontal loads to the top of the pier. In order to simplify the model, from the initial model, which includes all the superstructure and the substructure, we will bring only this substructure, and the weight of the superstructure will be applied as the point load in the bearing position. So from this model file, if we look at the model closely, so it has the additional load which is applied to the bearing position in order to consider the weight of the superstructure. And for considering the horizontal incremental loading in the pushover load, we apply this horizontal direction load. And in order to consider the eccentricity from the bridge center to this top of the pier table, additional eccentric moment has been considered. So this loading will be considered in our bridge pushover analysis. As mentioned, we consider the initial loading for the gravity direction dead load or superimposed dead load. From this, now we need to know the primary curve for the pushover analysis. For the general shape of the section, like the building, we can simply use the hinge property suggested from the FEMA or the Eurocode. But for the bridge section, when the section shape is quite irregular and the size of the section is very huge, in that case, we need to separately calculate the hinge primary curve. For this, we can also use the Midas GST, General Section Designer. So let's try to use Midas GST. So similarly, section analysis will be performed. And in Midas GST, for considering the nonlinear behavior, we can specify the material property for the reinforcements and the concrete with the various hysteresis model. For example, for the reinforcement, Mendel model has been considered, or we can specify it with the bilinear, parabola, rectangle model, Kenton-Park model, trilinear, bilinear, so on. For the reinforcement also, Park strain hardening model has been used, or we can use the bilinear, Minegoto-Pinto, or trilinear model. Then we need to know the axial force from this model for the column. So from the dead load, axial force of the column can be obtained. For example, 3700, sorry. And then from this, we can obtain this bilinear model. This bilinear model can be used in the pushover analysis. For this purpose, I'm going to connect Midas GST to Midas Civil and export this hinge position to Civil. When we export it, we need to specify the hinge length, which is also provided in Eurocode. How to calculate the hinge length? Hinge length can be obtained from the member length of the zero moment to the end of the section. And also we need to know the yield stress of the reinforcement and the bar diameter. So from this simple calculation, we can obtain the LP value, which is the hinge length. And this LP value that I have pre-calculated, I know the value length from the zero moment to the end of the section, and yield stress of the reinforcement and diameter of the reinforcement. So LP value has been calculated. This LP value, if we divide it with the entire length of the member, then we know the ratio. So 0.14 is the ratio compared to the member length. So if I want to bring it to my decibel, I will enter the proper hinge length, then apply. So my decibel will calculate the hinge property, and then it will be exported to my decibel. So now, previously we only had the global control and the pushover load case. Now we have the new hinge property. If we want to see the more details, there is also message window showing how the calculation is going on. So with the different axial force, the hinge property has been calculated and exported to Midas Civil. So in Midas Civil, if we see details, I have entered the hinge length, which is same in here, and my hinge property is applied here. And this hinge property, as it is the moment hinge, moment and the axial force interaction will be considered. So this value is all calculated and applied in the program. What I need to do is now I just want to assign the hinge property to my column. So assign the hinge property. Now I can perform pushover analysis. Pushover analysis is completed, and I can check the hinge curve. If we want to see the failure of the structure, we can also try to increase the maximum displacement, for example, 0.05. And you can see its behavior with the failure of the hinge. So we can know that our capacity displacement is 0.037. So this hinge curve has been obtained, and 0.037 is the capacity we have obtained from the Pushover hinge curve that I showed you here. And previously, from the response spectrum analysis, we have obtained the demand. And it will be compared. Ratio is 0.7, and we can say it is safe. So this is the procedure how we can assess the bridge from the response spectrum analysis for obtaining the demand and the pushover analysis for obtaining capacity. And as you can see, all the analysis was available with Civil, and even the capacity was calculated. Global verification has been done. Now we also want to verify the local demand, local deformation. So in the Eurocode, so local deformation can be verified by comparing the plastic rotation demand and plastic rotation capacity. Plastic rotation demands can be calculated from the analysis, and plastic rotation capacity is obtained from this formula, which is using the plastic capacity rotation from the formula obtained from here. So all this calculation is provided in Midas Civil. So what we need to do is simply compare the value in the table, code rotation table. So we have the plastic rotation demand in here and the capacity here. And when we compare these two, we need to divide it with the gamma value, which is the factor to reflect the local defect. Recommended value is 1.4. So what I can do is in the Excel file, I can bring this demand value, which was here, and I can bring the capacity value in here, and then I can divide my capacity with the gamma value. Then I can compare it with demand and capacity. So as the program provides you the capacity and demand, we can easily verify the local verification for the demand. So these were how we can perform the response spectrum or the pushover analysis with Midas Civil and how we can compare them. I would like to move to the next type of the seismic analysis, which is time history analysis. Time history analysis can be can be used with the different purpose. For example, we can use the time history analysis for estimating the boundary nonlinear isolator or damper, or in order to consider the material nonlinearity of the structure, we can perform inelastic time history analysis. And the linear time history or soil structure interaction fiber analysis can also be performed. So how to perform time history analysis? The procedure is not that complex in Midas server. We can consider the inelastic hinge or isolator first, and then time forcing function can be specified, and time history load case will be defined, ground acceleration, then finally perform time history analysis. So let's see with the program for that. So in this model, we have considered the nonlinear time history analysis. So what it needs to do is specify the time history load case with the number of time and the increments and damping, and nonlinear direct integration analysis will be performed. Time forcing function can be specified from our database, or if needed, we can also import any user-defined database. Then we can specify the scale factor, for example, considering the 130 rule, and also, if needed, we can specify the arrival time. Even different arrival time can be applied with the different function. In case of the long span bridge, for considering the multiple support extension. So let's say we have two different pier here and here, and the bridge length is very long. So we want to consider the different arrival time for the different function from here and in here. In that case, we can specify different function and also different arrival time. So multiple support extension can be considered. I have pre-performed the time history analysis. So, and in here, I have assigned the inelastic hinge property. This inelastic hinge property can be specified with different illustrating model. For example, kinematic hardening, and also this was applied for the axial components and the moment components. Axial force moment interaction is also considered. So from the analysis, we can check the behavior of the structure. We could see how the structure will be deformed with a different time. Even for the forces or the stress. And these results can also be obtained for the graph. So for the certain node, which is the top of the period table, we can see how the deformation will go on with the different time. And this time domain can also be changed to the frequent domain in order to obtain the maximum frequency. And also hysteretic curve can be checked. For example, for the y direction of the member, such hysteretic curve can be obtained. In order to consider the boundary nonlinearity, when we consider the structure as the linear behavior and we want to see the nonlinear boundaries, such as the viscous elastic damper, hysteretic system damper, or friction pendulum isolator, ledger bearing isolator. All of them can also be considered in Midas civil. For example, in this bridge, we have considered the ridge rubber bearing isolator. So we can specify their stiffness and the nonlinear behavior. And they were applied in this bearing position. So this red rubber bearing can be simulated in Midas civil. So similarly, we can check their behavior also with the graph. So from the pure top, how the displacement is going on with the time domain, or even for checking the maximum frequency with the frequent domain. And for the nonlinear divisor, the isolator, we can see their hysteretic curve as shown in here. So for the isolator, we can see their hysteretic curve, which is the general link number 3 that can be checked from here. So in this boundary nonlinear analysis, all the structure was considered with the elastic behavior. Then we have checked the nonlinear behavior of this isolator. Similarly, we can consider the viscous elastic damper, hysteretic system damper. And we already checked the inelastic time history model. So we considered the nonlinear behavior of the structure. And this hinge model can be specified with the kinematic hardening, Ductile, slim model, or multilinear model. Midas provides the various database for the earthquake list. So all different database of the earthquake record can be selected, or if required, we can copy and paste from the Excel file or import the user-defined function. And such graph results has been already checked. And this is the multiple support extension that I explained in the elastic time history model. So such long span bridge, the earthquake arrival time can be different, and even we want to consider the different function. So that can be considered using our multiple support extension. So specify desired function and arrival time, that's it. Also, the source stiffness interaction can be considered in our time history analysis, especially for the high seismic zone. You may want to consider the seismic analysis not only for the superstructure, but also the substructure as well. There's two ways. One is using the entire model with the substructure shown here, or we can consider the substructure with the condensed matrix stiffness. Using the general spring support, we can simulate this behavior. So 6 by 6 mass stiffness and damping matrix can be specified, as you can see from here. Then the behavior of the soil can be specified. That is called the general spring support function, or as mentioned, the entire pile can be modeled, even the different profile along with the depth of the pile can be entered, and then time history analysis can be performed to simulate this behavior. Finally, Midas provides fiber analysis. Fiber analysis is special because instead of performing detailed analysis using the plate or solid, we can simply model using the beam element as shown here, but we can try to divide the section. So the program can know where is the concrete, where is the reinforcement, and what is their material property with the behavior, this inelastic material model. Various databases provided, and then from this, fiber analysis can be performed. So we can check their nonlinear graph, the behavior graph, and with the different time step of the time history, how their state is going to be changed from the entirely elastic stage to the cracked stage. So such reinforcement is yield, and this part is still elastic, and such part is cracked. So from this 1D beam model, this is the simple beam model, 1D element, but we can also consider the nonlinear behavior from the time history analysis using this fiber analysis. So this is the old functionality that Midas will have in the seismic analysis. we have checked the response spectrum, pushover, and the time history analysis, including fiber analysis. If you have any question, please use the questions window. Thank you very much for your attention. Um, there is one question about the footbridge, the human-induced vibration of the steel structure. How we can consider this footbridge? I will show you one of the model file. So for the footbridge vibration analysis, this is not the model 1 second please. I want to show you with the sample model file. So what we can do is similarly performing the time history analysis, but this time instead of the earthquake forcing function, we want to consider with the foot working function. So this working function can be specified with a sine function in Midas GST, or we can use such working function. This sinusoidal function was used for considering the clouded load, or just a walking load or jogging load can be considered using such function. So what we will do is, using the dynamic nodal load, we apply the dynamic nodal load to this different position with the different arrival time. So apply this jogging load, which I showed you here. This jogging load is applied, for example, on this node in 3.3 seconds after a certain time, considering the speed of the jogging. On this node, 6.7 seconds, and this node, so on. So different arrival time, the such function will be applied and time history analysis will be performed. From that, we can similarly check the behavior of the bridge. I will show you with the animation. So we can check their behavior, or similarly we can obtain the graph from such time history analysis. And their displacement can also be checked from this graph. Another question for the adaptive pushover analysis. As of now, adaptive pushover analysis is not implemented in Midas 7. And the other question, how we can assign the diaphragm for the slab for the curved structure, curved slab, for example, or the inclined plate. Mm, for the diaphragm, so there is the various option in civil. For example, we can use the rigid link with the master and slave nodes, or we can also use the linear constraints. Linear constraint could be more appropriate for the irregular behavior, especially it has been developed for the curved bridge. So this linear constraint can be used. For more details, if you provide you any detailed picture, we can also give you some better detailed answer for this. The other question, can we use the SRSS combination for the XYZ direction, or only plus minus 30 rule is applied in Midas 7? In the load combination, so 130 rule can be automatically considered in Midas SV, but for the jet direction combination, manual combination will be required. For the jet direction, gravity direction combination, seismic loads, first of all, we can apply the response spectrum function for the all different direction, but the combination should be considered for different direction from the user. So in the dynamic loads, response spectrum load case, we can specify their direction in here, XY direction or Z direction. So desired direction can be specified. But the 100 circular will be applied for the X and Y direction. I guess I have entered all the questions. If you have any further question, please send us email. Anytime if you want to check capability of Midas server or on your project, you can contact us. Please send email to info@midasit.com. Then we are going to get back to you in short time. Thank you very much for your attention today. And I'm going to finish the webinar from here. Thank you.